So far, we've gone over the basic quantities and ideas behind circular motion, and one was the basic expression speed is 2 pi r f, or 2 pi r over the period to calculate the speed, incorporating the frequency and the period ideas from waves. Then we looked at, of course, centripetal acceleration being v squared over r, which of course is the attribute of the changing velocity as things are going around in circles, where it's about changing the direction, not necessarily how fast or slow. Now we're going to build on this even a little more, because of course change in v is associated with acceleration, but acceleration is also associated with something else. If we have some kind of acceleration, there must be a force, because in order to provide acceleration, you must have a force. And of course, that's just basically Newton's third law. So if we go to Newton's second law, if we go to basic F equals ma, that just applies to everything. That's just Newton's second law. It doesn't matter what kind of acceleration it is, it has to come from some kind of force. Well, if we specialize this a little bit, if we're talking about centripetal acceleration, that must then be centripetal force. And if we then take in the expression right here we have for centripetal acceleration and substitute it, we've got mv squared over r, which can then be used to calculate how much force is needed to get something to go in a circle. Because if you don't apply a force, you don't have an acceleration, you don't have a change in v, and you can't have it going in a circle. All right. Now, just like the acceleration points the same direction as the change in v, the force also has to point in the direction of the acceleration. So if you remember, the acceleration we had, this actually points to the center of the circle. Well, so does the force. This also has to point to the center of the circle, because the force and acceleration always go in the same direction. So it seems kind of weird, that the centripetal force would then go to the center of the circle, because most people think about, when things going in circles, think about flinging out. Well, you're not actually being flung out. The basic way to think about that for us, the easiest one for me has always been, if you've got a car and it's going on like a curve or something like that. So let's get a little car here. We've got a little tiny blue car, and the little tiny blue car is going around the curve. And we got a patch of ice on the road. Like people think they're being flung out when they go in a circle. Well, if this car all of a sudden hits the ice that's all over the highway, when that car then comes along, here, I'll get my little selection tool here. When that car comes along and goes around the circle, when it hits the ice and loses traction, it doesn't fling out sideways from the circle, because there's no force actually pushing out. If it hits the ice, it's just going to spiral out and just keep on going straight. That's generally the way it happens. And so now, it might curve a little bit, got a little bit of traction, but generally you hit the ice, you just lose all your traction, you go straight. And that's literally what's happening when things are going in circles, is they are just trying to go straight, but you pull in to the center of the circle in order to keep them going around. So nothing's actually being flung out. You're just trying to, or the object's just trying to go straight, and something pulls you in. It's sort of like if you have like something on a rope and you're whipping it around, you're spinning it around, spinning it around, spinning it around. If you let it go, it doesn't fling straight away from you. It keeps on going straight tangent to the circle that it was. And if you remember when we did the other stuff with the velocity vectors, that type of stuff, if we drew the velocity vector for this car, the velocity vector is tangent to the circle, something like that. So when it loses its traction or friction or grip on the tires because of the ice, it just keeps on trying to go straight. So no matter what, the acceleration, the force are actually pointing to the center of the circle. And if you ever thought about, like whipping something around, you are pulling towards yourself as the thing is going around. Now, of course, you feel, sort of it pulling out against you, which is actually Newton's third law. but that pulling out is just a reaction, so to speak, to you actually pulling in. So the objects aren't actually trying to fling out, they're just trying to go straight, and you end up pulling in. Now, what's kind of interesting about centripetal force in general is centripetal force doesn't actually exist on its own. Centripetal force actually comes from many actual sources. For example, we go to the car. What keeps the car on the road? What force keeps the car on the road, not including the ice? Well, of course, that's between the tires and the road. And what, of course, is between the tires and road? Well, of course, that is, the force of friction between the tires of the road. And of course, you lose the friction, that's when the car spins out and goes flying off the road. So things like friction, things like tension in a rope. If you're whipping something around in a rope, it could be tension. It could be a normal force where something's pushing on something going around a circle. There's lots of different things. It could even come from the force of gravity, with things like orbiting, like when satellites orbit or planets orbit the sun. There's lots of different things that actually provide the centripetal force. So when we're working with centripetal forces, a lot of it has to do with finding a force and then making that the centripetal force to find the circular motion stuff, or vice versa, use the circular motion stuff to find FC to attach then to other forces. So it's sort of like we've sort of got things like the 2 pi RF, and we've got the V squared over R. We sort of got that, like that circular motion stuff, and then we've got all these, things like friction and normal force. Oops, change that, not NN, but FN. You got things like normal force and FG and all these other forces. And what binds these two things together is centripetal force. So again, we'll find things like 2 pi RF and V squared over R to find FC, and then equate FC to other forces or reverse it. So it's kind of, because when you're finding FC or using FC, you've always got another force, because FC doesn't create itself. It's just it's sort of like the application of other forces to go in circular motion, but it's not actually the source of the force. All right, so sort of show how this works in a couple different scenarios and work with it a little bit. Okay, so let's take just a basic situation here, something really simple. All right, so let's just have a person here. They've got like a rope or something like that, and on that rope, oops. Make a little bigger. Later we'll give them like mittens or something like that. All right, let's say we got, I don't know. Here we go. Let's say we got a little pumpkin on a rope. There we go. Nice little pumpkin. All right, something like this. Okay. And let's say that the pumpkin is 1.2 kilograms. And let's say the rope is 2.8 meters long. And they're basically just whipping this thing around in a circle, okay, for whatever reason, who cares, doesn't matter. All right, so this is what they are doing. So we're going to just start by finding some simple things and work with a couple of things and see how the quantities kick together. So let's say that the pumpkin is moving at 3.5 meters per second. Okay, so let's do something really simple. So what's the frequency? Let's just start with that. So go kick back to some of the quantities you guys looked at before. So of course, frequency is connected to speed. So what you can do is you can use the 2 pi RF expression, that one that we've had before, and you can easily find out the frequency of this thing going around. And if we punch all those things out, we get about 0.20 hertz. Okay, so basically a fifth, actually, which then makes it really easy to find out the period, of course, because the period is the inverse of the frequency, and 1 over that, because they're inverses, 1 over that would then just be 5 seconds. Okay, so now let's introduce what we're talking before, like the new quantities and stuff like that. Let's just find the FC. All right, so of course, FC is mv squared over r. I mean, this just Basic practice, I've got my M, that's the 1.2. I'm going to multiply that by my V, which is 3.5. Don't forget to square that. And then divide by the radius. And if we do that, we can get a force of about 5.25 newtons. So that's how much force he's pulling in with along that rope. Now, of course, how do you do that? Well, when you pull in a rope, that's like tension. So the FC, this would be the tension in the rope. So that's what he's doing. He's pulling in on the rope, applying that tension, which then results in the circular motion. So that would be the FC in this case, so the force of tension. All right, so that's the basic way, the basic quantities and how this type of thing works. And of course, things spinning on chains and ropes and cables or swinging things, that's where it kicks in a lot of the time is tension. All right, okay, let's take another really simple, common type of scenario, and that would be with a car on the road. That's a really, really common thing to look at for this type of thing. So suppose we've got, circular path, okay, like a roundabout or a clover leaf when you're like changing directions to highway or something like that. A nice little sports car coming in here, nice little fancy car, nice little red car. All right, okay, come zooming along. And I'm going to go around. Let's say that the car is, let's say it's 1,800 kilogram car, and then let's say it's moving at 75 kilometers per hour, and let's say that it's going around, and well, actually, here, let's do it this way. Let's say it's using 23,000 newtons in order to go around the circle. Okay, and let's find the radius of the path. Okay, so it's using 23,000 newtons of force, so this would be my FC right there. I've got my 75 kilometers, but of course I want to change that into meters per second. So I'll convert that to 20.8 meters per second, and then we should be good to go. So of course, FC is mv squared over r. The only thing I don't have is the radius. I got the FC, the m, the v squared. So I'm just going to solve for the radius. And it looks like it's around, well, let's round up. We'll say it's around 34 meter radius. Okay, so the radius of the path would be about 34 meters. Now, where's that FC coming from? Well, we've talked about this a little before earlier on. Car going around a circle. This right here, that is, oops, I'm not sure what happened there, but that right there came from friction. Okay, hopefully that's fixed a little bit. This right here, this is coming from friction because it's the force of friction that keeps the car on the road. So if that is coming from the force of friction, which is of course the same thing right there, we can actually find out what is the coefficient of friction between the car and the road. So of course the coefficient of friction is FF over Fn, and in this case the friction is our FC, so that's that 23,000 newtons. And the normal force is just between the car and the road. And of course, normal force, just we'll say flat road, everything perfect, would just be the weight of the car. So if I take the 23,000 and I divide it by the weight of the car, I can get a coefficient of friction of about 1.3. Now this would be the effective using coefficient. I mean, the coefficient of friction between tires and road would be much higher than that, but this is like the effective or the coefficient of friction or the coefficient of friction actually being used to get this to work the way it does. Okay, so once again, FC connected to other forces, and then you can incorporate other ideas as well, and in this case, a little bit of coefficient of friction.